Good morning, students. So today we will talk about the statistics that distinguishes the two fundamental type of particles that we have discussed in the first class, the fermions and the bosons. We saw in the classical statistical mechanics that the particles are all given by Maxwell-Boltzmann statistics independent of whether they are independent of the type of the particles. But in the quantum world, when we are pushing towards high densities and low temperatures, the statistics of these particles are fundamentally different, and we will see today why. Okay. So, the agenda of today's lecture is statistics of fermions and bosons. Okay. Now, to derive the statistics, I will start with the partition function of a system of bosons and fermions, okay, that we have discussed in the last class. So, let us take the example of bosons first. So, I am going to take the case of bosons, and here we have already seen that these are classified as particles whose wave function, the wave function of the n particle system or the wave function of the n boson system, has an even parity. So, this essentially means that if I permute the particles in the system, the overall wave function does not change its sign, and this has natural consequences on the statistics it follows, and this is because the evenness of the parity operation allows an arbitrary number of bosons to sit in one energy level, and this is usually represented as the spin being an integer. So, they are classified as integer spin particles. Okay. And there is no restriction on the number of particles that can sit in a given energy level. I am going to say that as Nj, the number density or the it can only be, it can be any number between 0 and infinity. Okay. Number of particles in some energy level j. Okay. So, I can write down the partition function for this system. Under constant NVT conditions, okay, for n bosons as a summation over all the microstates, that is the possible values of these ni's which constitute a single microstate, and you sum over all possible values of such ni's into e raised to minus beta the Hamiltonian. So, this is your the Boltzmann factor. What is meant by summation over all possible excitations ni? Well, this summation is over all microstates. Okay. So, let us take off take one microstate here. So, the meaning of summation over ni is basically the fact that your sum over microstates. Okay. So, what is the sum, how is the sum implemented, how do we visualize in our heads this sum? Well, you take one microstate. So, I am going to write down one microstate. Let us say I am going to write down microstate mu 1. In this microstate you could have the energy levels, let us say you can have energy level 1, 2, 3, 4 and so on in infinite energy levels. Okay, these are number of energy levels are not they are basically uncountably large. And let us say in the microstate mu 1 I am having 3 bosons sitting in the first level, 1 boson sitting in second and 4 of them sitting here. So, basically for the microstate mu 1 I have n 1 equals to 3, n 2 equals to 1, n 3 equals to 4 and so on. But then the microstate can change, I can go to a mu 2 microstate where the population of these levels are different. So, again the first level, second level, third level, fourth level, and in this case let us say 1 particle sitting here, nothing sitting in 2, you got 5 sitting here and maybe 2 sitting here. So, now my n 1 is 1, n 2 is 0, n 3 is 5 and n 4 is equal to 2 and so on. So, this way you can change your microstates. So, the summation over microstates that I have written here is basically the summation over all possible sets of ni. So, for example, this would be mu 1 microstate would be the set with the values n 1 equal to 3, n 2 equal to 1, n 3 equal to 4 and so on. Then my set of excitations become n 1 equal to 1, n 2 equal to 0, n 3 equals to 5, n 4 equals to 2 and so on, and with the third microstate my set changes. So, that is the meaning of summation over all sets of ni. You take one set of ni's that is constituting your one microstate, then the set change. So, you are now looking at a different microstate and so on and so forth. So, that is the meaning of our partition function at constant NVT conditions. So, you have summation over all the sets of ni's, and our Boltzmann factor was e raised to minus beta, the Hamiltonian of that particularly chosen set in the summation. Okay. Now, the Hamiltonian of the microstate is given by nothing but the energy of the state multiplied by the number of guys sitting in that state. Okay. I will run from 1 to infinity because you have infinite energy levels in the system. Alright. So, let us plug this value here, and now I can write down my canonical partition function as summation over all possible sets of ni's into my Boltzmann factor, that is I am going to change the label here Nj, fine. Okay. J is just a label. Okay. Suppose I choose a microstate with n 1 equal to 2, n 2 equal to 3, then for that microstate you compute the Boltzmann factor. Okay. Now, this can be written as e to the power minus beta Okay. There are infinite terms here, but there is now a problem which becomes clear. So, I can write down this as the product of these exponents are taken here outside, okay, and the sum for each value of j that I take, okay, suppose j is 1, then I have this particular thing, but it has to have a sum over all the ni's. Okay. So, then I will take my nj going from 0 to n, because I have n fermions in the system, and this is basically e to the power minus beta Ej Nj, and it is very difficult to perform this sum simply because I have a restriction here. The sum is basically restricted to follow a constraint the total number of particles. So, I cannot take Nj arbitrarily from 0 to n for some j, because there is one other exponent corresponding to that pi j outside, where I can only take the values of n such that the sum of two n's are always constrained to become n. So, this constrained sum is very difficult to perform. Okay. So, this constrained summation is very hard to perform, meaning being the label Nj, which is the occupancy of jth level, cannot be independent taken from 0 to n for these exponents. Suppose I take Nj as n by 2 for the first exponential, the next exponential cannot have Nj anything other than what I am left with is basically I can't take it as n by 2 plus 1, and I have got infinite number of exponentials there. Okay. So, for each one of them the label Nj cannot take independent values, they are constrained to sum up to n, which is the number of particles in the system. So, I can't perform this summation, it is very hard. So, what is the solution? So, the solution is to shift the problem to the grand canonical ensemble, where n can change, okay, but it will keep the chemical potential constant. So, I am going to go to the grand canonical ensemble where number of particles in the system can change. This sum becomes unrestricted now, but now I have to conserve the chemical potential. So, let us shift to the grand canonical ensemble, which means now I will be computing the grand canonical partition function indicated here by two horizontal crosses on the function z. And as usual here I am going to write down my partition function as summation over all the microstates into e raised to minus beta the Hamiltonian of the microstate that is chosen by the summation here. Okay. Now, the Hamiltonian of the microstate in the grand canonical ensemble is nothing but summation over all the values of energy levels times the excitation of the level or number of particles sitting in that level, and multiplied by energy of that level minus Nj times chemical potential, because we have taken summation Nj as n for that particular microstate, because n itself is now changing. Okay. So, if you plug this in the above expression, our grand canonical partition function now becomes summation over all the microstates e raised to minus beta, and I am plugging the Hamiltonian here, summation j nj into Ej minus mu. Okay. As usual, the exponent is a sum. Okay. So, that becomes product outside. Okay. So, then I have for each j I will now take an unrestricted sum. So, this is the meaning of the unrestricted sum here. Now, for each exponential my nj can go from 0 to infinity. Okay. And this will be e to the power minus beta okay. So, now you have no problem. So, this is now an unrestricted sum. So, I can take in each exponent my label going from 0 to infinity, which I could not do previously. So, if you take 0 to infinity, then you can't do anything in the second one, because your n has been, you have to conserve the total number of particles. But here I do not have to conserve my number of particles, my n could be actually infinity, it could go up to infinity, which means each nj, which is independent of the other exponent, okay, can run from 0 to infinity without getting affected by the label in the next exponent. So, this is now an understood sum which can be performed very easily, because I am not conserving number of particles anymore. Okay. In the grand canonical ensemble, number of particles is not conserved. What is conserved basically chemical potential, volume and temperature, and that allows us to compute this sum in an unconstrained manner, which we could not do previously. Okay. So, then I can write down this as just pi j sum over all the j's, and for each j that I set outside I am going to write this sum inside for a few terms. So, I am going to take the first term for j equal to 0, n j equal to 0 is 1, then the second term is minus beta E j minus mu when n j becomes 1, and for the third term it is e raised to minus twice beta and so on. You have infinite terms here. Okay. As you can see, this is a geometric series. With the common ratio r as e to the power minus beta E j minus nu, okay, and the ratio of the successive terms in the limit n going to infinity converges for any value of beta E j and mu. So, this sum converges to the closed form 1 upon 1 minus the common ratio, which is e raised to minus beta E j minus mu. Okay. That is the converged sum. Fine. So, now I can realize this as my grand canonical partition function, and thank for the fact that the number of particles was not conserved, and I could perform this sum in the partition function in the unconstrained manner. So, before we proceed further, we would like to state here that the grand canonical ensemble is hence the natural choice of ensemble when you are doing quantum statistical calculations. So, when people say it is the ensemble to do correct enumeration of states, well, they are also saying this because it is also more convenient to compute the partition function. So, the fact that I could enumerate the states properly, which is due to the fact that the sum was performed in an unconstrained manner, makes the grand canonical ensemble a preferred choice for doing the calculations. Okay. So, that is why this is the preferred ensemble when you are doing quantum statistical mechanics. Okay. So, then let us take a logarithm on both sides, which we will be using it in the correspondence between classical to between quantum and classical statistical mechanics. So, let us just make a small note of the result. If you take logarithm on both sides, what we get is nothing but minus the logarithm of the products become sum, okay. And so, let us say that this is the result 1 and that is the result 2. So, we are now in a position to compute or to form the statistics of bosons. So, this discussion was for bosons. So, I am going to derive the average occupation number of bosons in some energy level J. Okay. So, deriving the statistics is now very straightforward. It is very easy now, and since you have followed the lectures in the first 2 chapters, you know how to compute average of any quantity if you know the distribution function in that corresponding ensemble. So, I know that my partition function is represented here, okay. Either you can take expression 1 or you can take the first expression here. Okay. So, I am going to write down the if I know the partition function, then certainly I know the probability of finding the microstate Ni. Okay. So, certainly I know the probability of a microstate, some collection of these Ni's is basically P of nu or P of these Ni's, okay, which constitutes a single microstate, and the probability of this single microstate is nothing but e raised to minus beta, the Hamiltonian of that microstate. Okay. So, therefore, if I want to know the average occupancy of some jth level, okay, this has to be normalized to the partition function. Okay. Otherwise, you do not sum these probabilities to 1 of the jth level. So, suppose I am interested in the average occupancy of the jth level, then this is nothing but summation over all the microstates, and what you essentially want to find out into okay. So, this means you want to basically compute this sum over all the microstates, but you are interested in only the jth level, number density in the jth level, into e raised to minus beta. I am now going to plug the form of the probability here, which is this. Okay. So, plug its form it is e raised to minus beta for some microstate that is summed over here, okay, divided by the grand canonical partition function. And this is very clear now. If I want to pull out a certain nj, okay, from all possible values of nj, then all I have to do, in fact it will become clear if I write down the Hamiltonian explicitly. So, the numerator is nothing but summation over all microstates nj e raised to minus beta summation over some, take a label p, and you take here np ep minus np into mu divided by okay. So, the NPs in the exponents are basically the values set by the microstate that you are choosing, you will sum over all the microstates. Now, if I want to pick the jth microstate nj, then I have to take the derivative with respect to okay, because in the summation here there will be one value of this p where p becomes j, only that value of nj will be taken out when you are taking derivative with respect to beta times ej, okay. All other values will go to 0 when they are taken derivative. So, I can write this as d over I can say that this summation is running over all microstates. So, I can simply take the derivative outside because it is for a fixed value of the state, and this is nothing but fine. Now, this is nothing but 1 upon z d over minus d beta E j of z. Okay. So, I can call this as the derivative of ln z, okay, because this quantity here is nothing but the partition function itself, sum over all the microstates e raised to minus beta into Hamiltonian, okay. This quantity is the canonical grand canonical partition function, okay. So, that is what I have done here, and now I can say that this is the expression for my average occupancy of the jth level. Let us call this as equation 3 and just plug the value of ln z from here, okay. So, because this is a lengthy expression, I am just going to copy it here so that you remember it. Okay. So, this is the expression for ln z. So, recalling that ln z is given as negative summation over ln 1 minus e raised to minus beta times E j minus mu. I can take the derivative and obtain n j, average value of n j. Okay. So, let us do the finish this derivative. So, I can write down for n j as only one term in this summation will contribute. Okay. So, we will have a minus sign outside over 1 minus e raised to minus beta, okay, and this minus will turn to plus, and what you will have is just e to the power minus beta E j minus mu, and you can simply write this as 1 over e to the power minus beta E j minus mu. We can no need to write the plus sign here, minus 1. So, this is the Fermi-Dirac this is the boson statistics, which is called as Bose-Einstein statistics. So, I am just going to write down B e to remind the user that this is the Bose-Einstein statistics for the system of bosons. Okay. So, this is going to be a very important result that we will be using in subsequent lectures. Okay. Deriving the statistics for fermions is also straightforward. Okay. So, you can derive for the system of fermions in a very straightforward manner. For fermions, we will have to start with the fact that the partition function in the grand canonical ensemble, of course, is still written by this expression. So, I am going to write down our partition function without altering much. So, here you can start from the same partition function. So, starting from the expression for the partition function in the grand canonical ensemble, you have to do this derivation slightly carefully, in the sense that now you are not expecting the system to to show more than one particle in a given energy level. So, the occupancy can be only 0 or 1 for a given energy level. Okay. So, basically these are particles with integer spins, half integer spins. Okay. So, the spins here are I will say these are in the vein of previous discussion, the spins are half integer, and I am going to say that these are particles whose system has a wave function that is antisymmetric in nature. So, the fermionic wave function has an odd parity. So, I am going to write this as a reminder here. and then I will say that we are starting from the same partition function, except for the fact that when you write down the summation on the right hand side as a product over all the j's, the summation on each n j is now taking values only 0 and 1. Okay, instead of going from 0 to infinity, this will now take only values 0 and 1. So, e to the power minus beta into n j e j minus mu will take the values only n j as 0 and 1. Okay. So, then if you write down, then what you get here is nothing but pi j okay. So, keep in mind here that for fermions because of the Pauli's exclusion principle. Okay. So, you may want to like we wrote in the previous discussion that the oddness of the parity operation on this system results into Pauli's exclusion principle. Okay. So, this is the systematic discussion that we have already done in the first lecture, that the two systems bosons and fermions differ from each other in the sense that one system has a wave function that is that has an even parity, the system of bosons, and the system of fermions has an odd parity, which means the parity operator for fermionic wave function has an eigenvalue minus 1, whereas the parity operator for the bosonic wave function has a bosonic systems has an eigenvalue plus 1. So, this basically means the following, that every time you permute two particles in a fermionic system, then the overall wave function incurs a negative sign. So, that basically means that you cannot, like we saw in the last lecture, you cannot take two particles to be in the same level, because that would make your Slater determinant to be 0, and that is the manifestation of Pauli's exclusion principle, that you cannot, your wave function will go to 0, which means you cannot see a realization where two particles are sitting in the same level. It will make your wave function to go to 0. So, the system of fermions half integer spins because they are odd parity wave function and they follow Pauli's exclusion principle, leads us to this definition of the grand canonical ensemble. So, we were doing the statistical mechanics purely from the directions from quantum mechanics, and that has led to this stage, and I can now take the logarithm of this and this would be nothing but summation over j's ln 1 plus e raised to minus beta e j minus mu. Okay. So, therefore, as usual, if somebody is interested in the average occupancy of fermions in some level j, then this is nothing but summation over all microstates. I need to sample n j in this distribution of microstates. Okay. And as before, I know that this is nothing but e to the power minus beta. The probability of finding a system in a microstate is given as the Boltzmann factor divided by partition function. So, this is my Hamiltonian, divided by a partition function. Okay. And hence mathematically this is nothing but 1 upon partition function d over minus beta E j as before the partition function. So, this is nothing but d over d minus beta E j of logarithm of the partition function. But now I will use the derivation of the partition function in the system of fermions. So, I am going to use this expression for ln z. Okay. So, plugging this expression in ln z, what do I get? Okay. So, I am going to plug this for this ln z. Okay. So, it will give me that is my left hand side, and please look at ln z here. So, in this summation only the jth term will contribute. J is running from 0 to infinity, the infinite energy levels in our system. Okay. Of that, out of those infinite levels, only one level j will contribute to this derivative, and that will give me 1 plus e raised to minus beta in the denominator, and I will have a e raised to minus beta E j minus mu in the numerator, and just multiplying and dividing by a common factor, I can write this as e raised to beta E j minus mu plus 1. Okay. So, then just to remind ourselves, this is nothing but Fermi-Dirac statistics. So, I can write this as combining both the results of the Fermi-Dirac and the Bose-Einstein statistics. I can write down combining both of them. So, let me call this as some equation. So far, yeah, combining. So, I am going to call this as Fermi-Dirac. So, combining both of them, I can finally write down a single expression for the average occupancy of the jth energy level as Fermi-Dirac or Bose-Einstein, as I can, in fact it is better that I use plus minus. Okay. So, plus for bosons and minus for fermions. I can write it as 1 upon e raised to beta E j minus mu plus minus 1. Okay. So, plus here corresponds to Fermi-Dirac statistics and the minus corresponds to Bose-Einstein statistics. Okay. So, fine. So, this comes so this brings to the end of our discussion on the Fermi-Dirac statistics, and when we meet next time we will talk about how these statistics decide the heat capacity of a solid at low temperatures due to both the vibrations of lattice ions and the free electrons of a conductor such as a copper, where we will see that the lattice contribution due to ions is proportional to T cube, and the free electron contribution is proportional to T, and this is a consequence of the Fermi-Dirac statistics and the Bose-Einstein statistics, that these electrons which are fermions follow, and the phonons which are the quantum of vibration of these ions follow. So, these two constituents, ions and electrons, satisfy different type of statistics, and hence their contribution to the overall heat capacity of low temperature solids are very different, and we shall see this in the next lecture. All right.